There's a photograph that tells an entire story in a single image. It shows two German soldiers standing atop a captured American tank, their faces etched with something between disbelief and despair. They're not smiling. They're not celebrating. They look broken. One of them has his hand on the hull, running his fingers along it almost reverently, as if trying to understand something through touch alone. That tank was called War Daddy 2, and in the spring of 1943, it would fundamentally change how Germany's best military minds understood the war they were losing. But by then, it was already far too late to act on that knowledge. Let me take you back to April 1943 to a place called Kummersdorf, a weapons testing facility located about 20 kilometers south of Berlin. This wasn't just any proving ground. Kummersdorf was the crown jewel of German military engineering, the place where the Reich tested its most advanced weapon systems. The German rocket program had been born here, under the watchful eye of engineers like Werner von Braun. Every major Wehrmacht weapon system had passed through these facilities. The best engineers in all of Germany worked in these labs, the men who had studied the captured Soviet T-34 tank in 1941 and helped design the Panther tank in response. These were the brilliant minds that Germany had mobilized to create technological masterpieces, and they were about to come face to face with something that would challenge everything they believed about their own superiority. The American tank sitting in the testing facility at Kummersdorf had a serial number painted on its hull, USA 3067641. The Americans had named it War Daddy 2 before it was abandoned on a North African battlefield 2 months earlier. German High Command wanted answers. They wanted to understand this machine. They wanted firing tables showing exactly where American tank armor was weak. They wanted to identify vulnerabilities that could be exploited. They wanted confirmation that German engineering was superior. What they were actually going to get was a blueprint for their own defeat. But before we get to what happened in that testing facility, we need to understand how a tank from North Africa found its way to Berlin and what it meant that it survived the journey. The battle that changed everything. It was February 1943 in Tunisia. The American army had tasted combat for the first time in Europe, and the experience was going poorly. The United States had sent the 1st Armored Division to North Africa to support Operation Torch, the invasion of French North Africa. These were American tankers who had trained in the peaceful American heartland, who had practiced in desert exercises in California, but who had never faced a determined enemy with superior tactics and better equipment. On February 14, 1943, they were about to get that education in the harshest possible way. The battle took place at Sidi Bou Zid, a small town in central Tunisia, that would become synonymous with American incompetence in the eyes of the German commanders who fought there. German panzer forces, commanded by experienced officers who had cut their teeth on the Eastern Front fighting the Soviets, smashed into the American position. The Germans had superior tactics, better command and control, and crews who understood how to use the terrain to their advantage. The American tankers, by contrast, were confused, poorly coordinated, and led by officers who didn't yet understand armored warfare. The Germans broke through the American lines with stunning efficiency. Tanks were abandoned, ammunition was lost, and the Americans fell back in what amounted to organized chaos. In the midst of this retreat, a Sherman tank from Company G, 3rd Battalion, 1st Armored Regiment, found itself stranded. Perhaps the crew ran out of fuel. Perhaps the transmission was damaged. Perhaps they took a hit that disabled the track and made the tank immobile. The historical record doesn't tell us exactly what happened, only that the crew had to abandon it. They left it behind as they raced back toward Kasserine Pass. It was a Sherman M4A1, armed with the standard 75mm gun and powered by a Continental R975 air-cooled radial engine. To German recovery teams, it was treasure. Unlike most captured tanks, this particular Sherman started on the first attempt. It ran, it functioned, and the Germans decided to take it home for examination. They drove War Daddy 2 across 200 miles of Tunisian desert, 200 miles on tank tracks through rough terrain, without a single mechanical failure. 4.5 days of driving, and the tank simply kept running. That itself should have been telling. That should have been a warning. German tanks regularly broke down after far shorter distances, But no one was paying attention to that detail. They loaded it onto a ship and sent it to Germany. When it arrived at Kummersdorf, the tank had survived a journey that would have destroyed most German tanks multiple times over. The arrogance. Before the fall, the German engineers approached War Daddy II with the confidence of men who had never been seriously challenged in their field. They had built the Tiger tank, with its fearsome 88-millimeter gun and thick armor that could turn aside almost any anti-tank weapon of the time. They had designed the Panther tank, a revolutionary design that, when it worked, was capable of devastating American armor at ranges where the American gun couldn't respond. They had created tank engines that were marvels of German precision manufacturing, complex machines that pushed the boundaries of what was technically possible. They were the best of the best, and they knew it. They had studied the captured Soviet T-34 tanks in 1941 and learned from that experience. What they expected to find in that American tank was evidence of inferior technology. They expected sloppy welds made by careless workers. They expected brittle steel that would shatter under impact. They expected crude mass production techniques that cut corners at every opportunity. They had their pens ready to write reports that would make the high command smile, reports that would confirm what everyone already knew. German engineering was not just superior, it was in a different category altogether. They began the systematic dismantling of War Daddy II with Prussian precision. They measured every armor plate carefully. They calculated every angle. They stenciled the numbers directly onto the hull in white paint, documenting everything with typical German methodical approach. The armor thickness was adequate but not impressive. 51 millimeters on the front hull, 38 millimeters on the sides. A Tiger tank could punch through this at over a mile of distance. So far, the expected narrative held. Then they opened the engine compartment, and things began to get uncomfortable. The engine that changed everything. Sitting in the rear of the Sherman's hull was a Continental R975 radial engine. This wasn't a tank engine at all. This was an airplane engine. The Americans had simply taken a proven aircraft power plant and adapted it for armored use. American aviation had advanced tremendously during the 1930s, and aircraft engines had become reliable workhorses. The Americans had the brilliant pragmatism to realize that if something works reliably in an airplane flying at 30,000 feet where you can't reach it for hours, it would work perfectly in a tank where mechanics were standing right next to it. This kind of thinking, taking proven technology and applying it in new ways, was typical of American engineering philosophy. The Continental R975 produced 400 horsepower. It was air-cooled, which meant it didn't require the complex cooling systems of liquid-cooled engines. It was designed for reliability at altitude where mechanics couldn't reach it during flight. It was robust, proven through thousands of hours of actual operation, and surprisingly simple for something so powerful. The Sherman, which weighed 30 tons, had a power-to-weight ratio of 13 horsepower per ton. The Panther, by contrast, weighed 45 tons and produced 700 horsepower, giving it only 15.5 horsepower per ton. This meant Germany's vaunted engineering gave them only a marginal advantage, and it came at an enormous cost in complexity. The German engineers began taking detailed notes. They weren't just documenting specifications, they were beginning to understand something fundamentally troubling about the American approach. That cost of complexity was everywhere. The Continental engine could be serviced in the field by mechanics with basic training. Major components were accessible through large hatches that swung open easily. Oil changes took minutes. Anyone could do it. Spark plug replacement required no special tools. A Sherman could be maintained almost anywhere by almost anyone with minimal technical knowledge. It was almost primitive in its simplicity, which was precisely the point. In contrast, the Maybach HL230 engine that powered the Panther was an engineering marvel. It was compact, powerful, and technically superior in almost every measurable way. But it had known cooling problems. It was prone to catching fire. It required constant maintenance from specialists. When one needed replacement, you couldn't just unbolt it and lift it out. You had to bring in a crane and spend a full day removing and installing it. German tank engines required factory-trained specialists for routine maintenance. A simple oil change required disassembly of systems that an American tank mechanic would never dream of touching. The German engineers began to understand something deeply troubling. The American philosophy wasn't wrong. It wasn't crude or inferior. It was just different. It was deliberately trading some maximum performance for something they valued more: availability. That realization struck at the heart of everything German military engineering had been built upon. But at this point, most of the engineers still assumed that the American approach was a mistake, that performance would ultimately matter more than availability. The sound that revealed the truth. When they ran the powertrain, when they tested the transmission and gearbox through its full range of motions, the German engineers expected to hear the familiar high-pitched whine of spur gears fighting against friction. It was a sound they knew intimately from their own tanks, the sound of gears under stress, tooth grinding against tooth. They were so familiar with that sound that they had probably stopped hearing it consciously. It was just the normal sound of a tank operating. But the Sherman didn't whine. It hummed. It hummed with an almost musical quality, a smooth, almost pleasant sound that suggested gears working together in harmony rather than struggling against each other. One engineer called his colleagues over, unable to believe what he was hearing. He wanted them to experience this with their own ears, to understand what he was hearing. The Americans had used herringbone gears, precision-cut helical teeth that meshed smoothly under load, the kind of gears that lasted for thousands of miles without significant wear. The teeth were angled in a distinctive V-shaped pattern that distributed stress across multiple teeth at the same time, spreading the load and reducing the pressure on any individual tooth. German tanks, by contrast, used spur gears. These had straight-cut teeth running parallel to the axis of the shaft. They were simpler to cut, cheaper to manufacture, and they engaged with a sudden shock that created the characteristic whine. They wore out quickly under combat driving, where tanks were constantly accelerating, decelerating, and changing direction at high speeds. Why did Germany use spur gears when herringbone gears were so clearly superior? The reason was grimly practical. Herringbone gears required complex machining and specialized gear-cutting tools. Those tools used tungsten carbide, a strategic material in desperately short supply in Germany due to the Allied blockade. With their industry cut off from global supply chains, with critical raw materials becoming increasingly difficult to obtain, Germany had made a choice: use spur gears to conserve tungsten carbide and reduce tooling wear. It was the right decision given Germany's circumstances, but it meant accepting transmission systems that were fundamentally inferior. The numbers the German engineers documented were devastating. The Sherman's transmission could handle 3,000 kilometers before needing a major overhaul. The Panthers' final drive, which consisted of 2 cascaded spur gear reduction sets, had an average lifespan of about 100 kilometers. Not 100,000 kilometers, 100. Under heavy use, a Panther crew had to assume that after traveling 100 kilometers from the railhead, the final drive might fail. A Sherman crew, by contrast, could reasonably expect their transmission to last through weeks of continuous operations. A Sherman could theoretically drive from Normandy to Berlin under its own power, covering more than 1,000 kilometers. A Panther could barely make it from the rail yard to the front lines. This was not a minor difference. This was the difference between a mobile weapon of war and a static gun platform that happened to have tracks underneath it. The implications were staggering. German tank doctrine was built around mobile armored warfare, on the ability to concentrate armor at decisive points quickly. But if your tanks could only travel 100 kilometers before their transmissions failed, you were essentially tethered to your railheads. You were forced into the very kind of static, positional warfare that favored a numerically superior enemy. The German engineers who understood metallurgy and manufacturing processes recognized what they were seeing. This wasn't just a design choice. This was a fundamental difference in manufacturing capability. America had the industrial capacity to produce millions of herringbone gears with the precision required. They had access to tungsten carbide and other strategic materials. They had the infrastructure, the trained workers, the machine tools, and the supply chains necessary to build complex precision components consistently and reliably. Germany, despite having brilliant engineers, did not have these resources anymore. The blockade was slowly strangling German industry. The stabilizer that seemed impossible. But the engineers hadn't finished their examination. They found something else in War Daddy 2 that made them understand just how far behind Germany had fallen in certain areas of technology. On the 75mm gun, there was a small box attached to its mounting. Electrical cables ran from this box to a gyroscope located near the gunner's position. It was a gun stabilizer, a gyroscopic stabilization system in a mass-produced tank. This wasn't supposed to exist, not yet, not at this stage of the war. The German engineers had experimented with stabilizers. They had dreamed of putting them in their tanks. They understood the tactical advantage such a system would provide. Imagine being able to fire accurately at a moving target without stopping. Imagine being able to maintain aim even as your tank bounced over rough terrain. This was the future of tank warfare, the next generation of technology that would give whoever possessed it an overwhelming advantage. But they had never managed to miniaturize the components enough. The precision required was simply beyond their current manufacturing capabilities. The gyroscopes had to be incredibly precise. The servo motors had to respond instantly and smoothly. The electrical systems had to be perfectly integrated with the mechanical firing mechanism. Creating all of this in a compact package that could fit in a tank turret was supposed to be impossible with current German manufacturing techniques. And yet, here it was, in an American tank that Germany considered to be a medium tank with an inferior gun. The Westinghouse system they had installed wasn't perfect, the engineers noted. It only stabilized in the vertical plane. It couldn't provide true shoot-on-the-move accuracy in the modern sense that stabilization would eventually provide. But it did something far more valuable than perfection. It kept the gun roughly on target while the tank moved. This meant a Sherman gunner could fire accurately within seconds of stopping. A German tank crew needed 10 to 15 seconds for their suspension to settle, for the gun to stabilize, for them to get the gun properly aimed and ready to fire. In a tank duel, and all armored combat consists of a series of individual tank duels. The first accurate shot usually won. The side that got their round off first almost always had the advantage. The Sherman could get that crucial first shot off before a German tank had even stopped bouncing from the acceleration. The German engineers examined the gyroscope and servo motors closely. They calculated what it would take to replicate this system in a German tank. What kind of manufacturing precision would be required? What materials would they need? How many machine tools would they have to dedicate to production? The answer they reached was the same answer they came to repeatedly during this examination. They couldn't. Not with their current industrial base, not with the materials available to them, not with the precision manufacturing they had. And more importantly, they realized they wouldn't be able to develop this capability in any reasonable time frame. American manufacturing had advanced so far beyond what Germany could achieve that the gap seemed unbridgeable. It wasn't that American engineers were smarter than German engineers. It was that American factories, with their access to unlimited resources, unlimited electrical power, unlimited raw materials, and their production line manufacturing philosophy, could achieve things that German craftsmanship simply couldn't match. The demonstration that sealed Germany's fate. In June 1943, War Daddy 2 was transferred to the Hillersleben artillery range for a demonstration before the High Command. This wasn't just another test. This was a carefully choreographed event where German generals gathered to watch. Men who controlled armored production priorities, officers who would decide whether to continue building Tigers and Panthers or potentially change direction entirely. The German High Command wanted a show. They wanted to be impressed. What they were going to get was a spectacle that would confirm every wrong instinct they already held. The demonstration organizers set up a hill climbing test, a steep 30-degree slope of loose sand. This was challenging terrain designed to test the mobility and power of tanks. The Panther went first. The German tank roared up the hill with what seemed like effortless power. Its wide tracks, designed for cross-country flotation, bit into the sand with authority. Its powerful 700-horsepower Maybach engine never strained, never faltered. It climbed the slope as if the terrain meant nothing. The generals smiled. They saw what they wanted to see: Proof that German tanks were technically superior. Proof that German engineering and German power could overcome any obstacle. Then came War Daddy 2. Its narrower rubber block tracks, designed primarily for road marching rather than cross-country terrain, began to slip on the loose sandy surface. The Continental engine wheezed under the strain. The track spun ineffectively. The tank slid backward. The Sherman failed to climb the hill. The Sherman slid back down. Generals applauded and congratulated each other. The demonstration had proven exactly what they wanted to believe. American tanks were inferior, German tanks were superior. But the demonstration had revealed something different to the engineers watching. The engineers looked at the transmission and saw a warning that no one wanted to hear. Yes, the Panther could climb that hill. Yes, it could demonstrate impressive performance on a carefully selected test slope. But the engineers knew something crucial the generals didn't understand, or didn't want to understand. The Panther had just spent significant effort climbing that hill, and every moment of that effort was stressing the transmission, the final drive, the running gear, systems that they knew were already at the limit of their durability. The Sherman had failed on that slope, but the engineers who had spent weeks examining War Daddy 2 knew it had just driven 200 miles across the Tunisian desert under its own power. Real-world operational conditions, not a carefully arranged demonstration. The Panther could rarely make that journey without catastrophic failure. The failure on the hill at Hillersleben was a disaster, but not for the Americans. It was a disaster for Germany. The generals looked at that sandy slope and saw victory. The engineers looked at the transmissions and saw the future of the war. The Panther had won the sprint, but the engineers knew it would never survive the marathon. While the Sherman couldn't climb that specific sandy slope, it had proven through actual operational endurance that it could travel the distances that mattered in real warfare. The hill climb validated every wrong instinct the German military had developed. It convinced them to keep building high-performance thoroughbreds instead of reliable workhorses. The engineers who had spent weeks inside War Daddy 2's compartments knew the truth, but they had just watched their generals cheer as the Sherman slid backward. On loose sand. Nobody wanted to hear that the American tank's failure on the hill meant nothing compared to its success getting to the hill in the first place. Albert Speer's haunting realization. Then Albert Speer came to see for himself. Speer was the Reich Minister of Armaments, the man who controlled German war production. He had tripled German weapons production in 1942 through reorganization and streamlining. He believed German engineering could outproduce the Allies if properly managed. He was brilliant, efficient, and completely committed to the German war effort. But he was also someone who could think in terms beyond pure engineering specifications. Photographs exist of Speer examining War Daddy 2. He studied the reports, he talked to the engineers, and he reached a conclusion that would haunt him for the rest of his life. Years later, after the war had ended in catastrophe, Speer wrote in his memoir about reports from Italy that praised the Sherman's cross-country mobility. The American tank climbed mountains that German experts considered inaccessible to armor. The engine's power-to-weight ratio gave it superior mobility on level ground compared to German designs. But Speer understood the deeper problem. Germany was building complex machines that required a dedicated rail network to move. America was building a mobile force that could drive itself to the front line. Speer realized that no amount of German engineering genius could overcome a logistical philosophy that was simply better. The Sherman wasn't just a tank, it was a philosophy. American industrial philosophy prioritized three things: reliability, maintainability, and mass production. German industrial philosophy prioritized one thing: technical superiority. American designers had made different choices. They accepted a less powerful gun because the 75mm was reliable and ammunition was plentiful. They accepted thinner armor because it reduced weight and improved mobility. They accepted a simpler design because it meant faster production and easier maintenance. Germany couldn't compete with that. Not because German engineers weren't brilliant, they were. Germany couldn't compete because German engineers had optimized for the wrong things. The reality of operational readiness. By 1944, the truth that the engineers at Kummersdorf had foreseen became blindingly obvious. German armored divisions reported operational readiness rates of 35 to 45%. This meant that at any given moment, more than half of Germany's tanks were broken down, sitting in repair shops, waiting for parts that might not arrive, or suffering from maintenance problems that couldn't be fixed in field conditions. More than half their tanks were broken down at any given time. American armored units, by contrast, maintained readiness rates consistently above 85%. This wasn't a minor difference. This was the difference between having a functional army and having a collection of expensive machines that couldn't fight. The implications were staggering. When Germany needed to launch an offensive, they had to cannibalize tanks that were temporarily broken down just to get enough vehicles operational. When America needed tanks for an offensive, they had tanks. They had enough tanks operational to attack. They had enough tanks in reserve. The numbers told a story that German propaganda tried desperately to hide. The operational readiness problem wasn't theoretical. It manifested in concrete ways on every battlefield. During the Normandy campaign, roughly half of all abandoned Panther tanks had been destroyed by their own crews after mechanical breakdowns. Not combat damage, mechanical failure. German tankers had disabled their vehicles and blown them up to prevent capture because they couldn't be repaired in the field. The recovery vehicles were broken down too. Imagine the frustration of a German Panther crew. You have the most powerful gun on the battlefield. You have the thickest armor, but you're standing on the side of a road in France watching your transmission smoke while a column of Shermans drives past you. The Americans lose some tanks in combat, but they keep moving. You know they're going to win this war. By late 1944, the statistics became even more dramatic. 60 to 70% of German heavy tank losses were non-combat related. Fuel shortages and breakdowns, not American gunfire. The engineers at Kummersdorf had seen this coming. They had documented every advantage the Sherman offered and written reports explaining exactly why American mass production would win the logistics war. Nobody listened. The generals had watched the Sherman fail on a sandy slope and walked away confident that German engineering was superior. In January 1945, the Panzer Commission submitted a report almost desperate in its tone. 500 defective Panzer IV final drives, 370 defective Panther drives, 100 Tiger failures. These were actual reported failures from units in the field, not estimates. Troops were losing confidence. In some situations, they were abandoning entire vehicles just because of transmission problems. German officers reported that their men's morale was declining as they realized their tanks were more likely to strand them than their enemies were to destroy them. Why Germany couldn't change course? Germany couldn't adopt American manufacturing philosophy for reasons that went far beyond pure engineering capability. The strategic materials weren't available anymore. Herringbone gears required complex tooling that Germany lacked the capacity to produce. Precision electronics required copper and rare earth elements that were becoming increasingly scarce. Allied blockades had cut Germany off from global supply chains, choking off the flow of critical materials that German industry depended upon. The production culture couldn't change fast enough. German factories had been built around the principle of skilled craftsmen who hand-fitted components to each other with meticulous precision. American factories, by contrast, used interchangeable parts and assembly line manufacturing. Converting one system to the other would have required years of retooling, years of training workers in new methods, years of reorganizing factories from the ground up. Germany didn't have years. Germany was losing the war, and everyone knew it. But there was something else, something even more fundamental that prevented Germany from changing course. The Nazi ideology got in the way. German engineering was supposed to be superior. It was supposed to represent the technical superiority of the Aryan race. Admitting that American mass production techniques were actually better, that American factories, powered by workers that Nazi ideology considered racially inferior, were producing weapons that outperformed German designs, contradicted everything the regime believed and had been telling its people. How could you tell the German people that American factories were doing something better than German factories? How could you admit that quantity combined with clever design was beating quality and complexity? It was politically impossible. It undermined the entire justification for Nazi racial superiority. So Germany kept building Tigers and Panthers, magnificent machines, technical marvels. tanks that spent more time broken down than fighting. Germany remained trapped, bound by an ideology that demanded perfection and an industrial base that could no longer afford the cost of that perfection. They built engineering masterpieces in small numbers, while America built reliable machines in staggering quantities. It wasn't a question of which tanks were better. It was a question of which philosophy would win a war of attrition against an enemy with unlimited resources, unlimited industrial capacity, and the willingness to accept good enough if it meant producing 10 times as many machines. The final accounting America built 49,324 Sherman tanks during the war. That number almost seems incomprehensible. Nearly 50,000 tanks. Germany built approximately 6,000 Panthers and 1,347 Tigers combined. The production ratio was nearly 8-to-1 for medium tanks alone. And that doesn't even count the hundreds of other German tank types like Panzer IVs, Panzer IIIs, and tank destroyers. And American tanks actually worked when they reached the front. A Tiger could destroy 5 Shermans in a single engagement. That statistical advantage is true and impressive. German tankers achieved kill ratios that became legendary. Individual German tank crews, especially the experienced veterans from the Eastern Front, demonstrated skills that made them feared opponents. But there was a fundamental flaw in that calculation. The Allies had 6 more Shermans arriving tomorrow, and the Tiger would be broken down, waiting for a transmission that wouldn't arrive for 3 weeks. The Tiger crew was wondering if they'd even have a tank by then, or if they'd be transferred to infantry duties because there weren't enough operational tanks. The mathematics were brutal and inescapable. German tankers achieved kill ratios that would have won any other war. But this particular war wasn't about kill ratios. It was about logistics. It was about which nation could produce reliable machines that actually worked in sustained combat operations. It was about which side could keep tanks in the field long enough to accomplish strategic objectives. War Daddy 2 had shown the German engineers exactly why they would lose. A tank that started when you pushed the button, a transmission that lasted the life of the tank, an engine that any mechanic with basic training could service, a gun stabilizer that allowed accurate fire without stopping, design choices that prioritized availability over maximum performance. Reliability beats perfection every single time. Availability beats capability every single time. Working beats superior every single time. The engineers at Kummersdorf knew this truth. They had documented everything. They had written reports explaining exactly why American mass production philosophy would win the logistics war. But nobody in the high command wanted to hear it. The generals had watched the Sherman fail on a sandy slope and walked away confident that German engineering was superior. They had chosen to believe what they wanted to believe rather than understand what they were seeing. And so the war continued. Germany kept building its magnificent machines. America kept building its reliable workhorses. The outcome was never really in doubt. If you found this story as fascinating as I did, I'd love for you to like and subscribe to WW2 Archives. There are countless more stories about the people, the machines, and the choices that shaped World War II. Each one offers lessons about strategy, manufacturing, human nature, and the price of ideology. Thanks for joining me on this journey through history.